modern kitchen is a space of predictable comfort. Precise temperature control, carefully designed ergonomics, and safety are paramount. We take this for granted. However, if we travel back in time to the heart of an English castle in the High Middle Ages, the concept of a kitchen takes on a completely different meaning. It is not a room for cooking. It is an industrial workshop, almost a blast furnace enclosed in stone. A huge, echoing space filled with heat, steam, and constant activity, where temperature control was not a matter of turning a knob, but a complex engineering task. Romantic notions of the Middle Ages often paint pictures of cozy hearths. The castle kitchen had nothing to do with that. It was a thermodynamic system operating at the limits of materials and human endurance. It was not designed for comfort, but for productivity and, more importantly, for the safety of the entire castle. Mistakes in this system could have catastrophic consequences. Watch the video to the end to find out how medieval engineers and chefs controlled the fiery element trapped within stone and what invisible systems worked to keep the castle fed. Contrary to popular belief, which was shaped by later, more compact buildings, the kitchen in a large English castle of the 12th to 14th centuries was rarely located in the main tower or keep. It was most often built as a separate, freestanding building within the fortress walls, as confirmed by numerous archaeological finds of the foundations of such structures. The most striking surviving example of this architecture is the famous octagonal abbot's kitchen at Glastonbury, built in the 14th century. This decision was dictated not by convenience, but by cold and pragmatic risk management logic, as the kitchen was the main source of open fire in the castle, and an uncontrolled fire, fueled by large amounts of boiling fat and cooking oils, was the #1 threat. The loss of the castle to fire was not just a domestic tragedy, but a catastrophic military and economic defeat that could undermine the power of any feudal lord. Moving the kitchen to a separate building, a kind of fire pavilion, was a key element of the security system, which localized the greatest danger, preventing it from spreading to the armory, living quarters, and treasury. This fear of fire was entirely justified and reinforced by bitter experience. The chronicles of the time are full of reports of devastating fires. For example, in 1174, the famous Canterbury Cathedral was almost destroyed by a fire that started with sparks falling on the wooden roof. If even a great cathedral built of stone could suffer such damage, the threat to a castle full of wooden floors, furniture, and tapestries was even more real. Roofing materials such as wooden shingles or straw were highly flammable. Sparks flying out of wide kitchen chimneys could easily set fire to the roofs of neighboring buildings. Inside the castle, tons of flammable materials were stored. Flour, whose dust could be explosive, fabrics, and hay supplies. Firefighting methods were primitive and consisted of creating human chains to pass buckets of water from a well or moat, which was completely ineffective against large-scale fires. Therefore, isolation was the only reliable strategy. The kitchen at Glastonbury, with its 4 huge corner fireplaces, is the epitome of this idea. A veritable fortress for fire, designed to burn itself down in the event of an incident without affecting the priceless buildings of the abbey. Such pavilion kitchens were usually connected to the Great Hall, where feasts were held by covered galleries. These passageways, known as pentacies, were simple but functional canopies on wooden or stone pillars attached to the hall wall. It protected not only the dishes from cooling and bad weather during transport, but also the servants themselves, who moved continuously between the kitchen and the hall. The pentaci also served as a social and sensory buffer, separating the noise, smells, and intense heat of the kitchen from the noble atmosphere of the Great Hall. The design of the kitchen itself was also based on the idea of fire containment. The walls were built of stone and were up to 1.5 meters thick, and the ceiling was often not made of wooden beams, but of a heavy stone vault capable of withstanding extreme heat and preventing flames from spreading to the roof. Heavy stone slabs or ceramic tiles were used for the roof instead of combustible straw. The octagonal or circular shape, as in Glastonbury, was not an architectural refinement, but a functional solution. It provided better structural stability than a square structure and allowed several hearths to be placed around the perimeter of the walls. with smoke effectively converging on a single vent in the center of the roof. Thus, the first and foremost principle of kitchen heating was not how to create it, but how to safely isolate it from the rest of the world. What safety principles from medieval architecture, in particular the principle of isolating hazardous objects, do you think are still relevant in modern industrial construction? Write your opinion in the comments. The central element of any castle kitchen was the great hearth. Its size, recorded in archaeological finds, for example, in the castles of Durham or Carnarvon, is mind-boggling. It was not just a niche in the wall, but an entire architectural system, essentially a separate room within a room. The depth of such a hearth could reach 2 to 3 meters, and its width could be 4 to 5 meters, allowing an adult to freely enter it for cleaning or to control the complex system of spits. In such a space, as described in medieval chronicles, it was possible to simultaneously roast 2 or 3 oxen on spits, cook food in several suspended cauldrons, and bake smaller dishes directly in the hot ashes. The hearth was the heart of the kitchen, its main heat source, which operated almost non-stop, especially during preparations for large feasts such as Christmas or Easter. It was fueled not just by logs but by entire sections of tree trunks, which several people struggled to drag inside. These huge logs, known as backlogs, were stacked against the back wall of the hearth and could smolder all day, creating a constant source of heat. Structurally, the great hearth was a massive stone structure that extended deep into the wall and foundation. For its interior, the floor where the fire burned, a special fireproof stone or early forms of fire brick were often used, capable of withstanding extreme temperatures and not cracking. The floor itself was not flat. It was deliberately laid at a slight angle forward toward a special channel or trough. This channel was designed to collect and drain the boiling fat that dripped in huge quantities from the roasting meat. This was not only a way to collect a valuable product for further use, but also an essential safety feature that prevented fat from accumulating near the fire and suddenly igniting. This stone mass served as a heat accumulator. It absorbed the intense heat of the open flame and converted it into stable, gentle, radiant heat, which it then slowly and evenly released into the room. Above the hearth was a huge smoke hood, often made of stone or a wattle and daub frame, a technique involving a woven frame covered with clay. Its funnel-shaped design, carefully calculated, created a powerful, steady draft that literally sucked smoke and steam into a wide chimney. In the largest kitchens, such as those at Hampton Court, there were several of these great hearths. The presence of 2 hearths located opposite each other made it possible to create 2 independent workstations. One could specialize in roasting meat on spits, the roast, the other in cooking soups, stews, and sauces in cauldrons, the boil. This was division of labor in its medieval sense. Even in a single hearth, master chefs created several temperature zones. A strong flame was maintained in the center for the main spit. To the side, a mountain of hot coals was raked together for cooking on a gridiron, and in the farthest and coolest corners, pots requiring slow simmering stood on trivets. The heat was so intense that the cooks had to wear shoes with thick wooden soles to protect their feet from the hot stone floor and constantly wet their faces with water. Controlling the fire in such a hearth was an art mastered by the head chef or a servant appointed by him. But such a giant consumer of energy required an appropriate supply. What, and more importantly, how much fuel was used to heat this monster? The biggest problem with the giant hearth was not the heat, but the smoke mixed with greasy vapors. A conventional chimney, even the widest one, could not always cope with the enormous volume of combustion products produced by the continuously burning fire. The smoke in the kitchen made work not just uncomfortable, but physically impossible. To solve this problem, medieval engineers used a passive ventilation system that was ingenious in its simplicity and based on the laws of convection. This was a significant step forward compared to the simple smoke vent in the roof of an early medieval dwelling. The physical principle behind this solution is known as the stack effect. The higher the column of hot air, the greater the negative pressure at its base, and the more active the inflow of cold air to replace it. The entire architecture of the kitchen was designed to maximize this effect. The ceilings in castle kitchens, such as in the preserved kitchen of Durham Castle, were very high, often vaulted, reaching heights of 10-15 meters. This height was not a whim, but a key working parameter. At the highest point of the roof, directly above the center of the room, there was a special deflector lantern, or louver. A beautiful example of such a device can be seen on the roof of the kitchen at Glastonbury Abbey. It was an octagonal stone or wooden tower with sloping louvers that allowed air to escape but protected against rain and snow. The design of the louvers was critically important. They directed rainwater outside, preventing it from flooding the kitchen. The system worked as follows. Hot air and smoke from the hearths, being lighter, rose to the ceiling. There they accumulated under the arches and escaped outside through the louvers, creating a visible column of steam. This process can be imagined as the creation of an artificial, constantly operating upward flow that turned the entire kitchen building into one huge exhaust pipe. At the same time, the warm air escaping created a zone of low pressure in the room. This in turn caused colder and denser outside air to flow in through low-lying windows, doorways, and special unglazed ventilation openings near the floor, often referred to as cat flaps. The location and size of these air vents were carefully calculated. 2 large vents would have created strong drafts at floor level, interfering with work and causing uncontrolled flare-ups in the hearths. 2 small vents would not have provided sufficient draft. These openings were often not located directly opposite the fireplaces, but in the corners, so that the incoming air had time to mix with the warm air in the room before reaching the fire. This created a constant, directed airflow from the bottom up. This invisible engine ensured effective smoke removal without any mechanical devices. The system was so successful that it kept the air relatively clean, even when several hearths were operating at full capacity. This turned the kitchen into a huge ventilation shaft powered by its own energy. Wood was the main fuel for large hearths. The demand for it was enormous, as confirmed by household records, for example, from the estates of the Earl of Lancaster. The castle kitchen could burn several cartloads of wood a day. This required the creation of a complex system of procurement and logistics, managed by a special official called a woodward or forester. The castle usually owned the right to harvest wood, estover, where teams of woodcutters used heavy felling axes and billhooks to cut down trees. The wood had to be not only cut down, but also properly prepared. To get the most heat and the least smoke, the wood had to be dry, so it was kept in wood piles for at least a year. The supply of firewood for the castle in winter was a strategic resource, no less important than grain reserves, since without fuel it would be impossible to bake bread from this grain. In the event of a siege, the castle would be cut off from the forest lands, and the internal supply of firewood would become the only source of heat for cooking. Woodward not only supervised the felling, but also managed the forestry, often using a system known as coppicing. This is a method of sustainable forest management in which trees such as hazel or ash are cut down to the stump, which stimulates the growth of numerous new shoots. These shoots grew quickly and after a few years provided fuel of the ideal size, while the tree itself remained alive. This ensured a constant and renewable source of wood. Special sledges or carts were used to harvest and transport the wood. Inside the castle, there were huge wood sheds where the main supply was stored. Preference was given to hardwoods such as oak, beech, or ash. They burned slowly and evenly and produced a lot of hot coals, which were ideal for long cooking. In addition to firewood, charcoal was also widely used. It was produced in the forest by specialist charcoal burners, colliers, by slowly burning wood in earth pits or clamps with limited access to oxygen. This labor-intensive process, which lasted several days, required constant supervision. Charcoal was a more expensive fuel, but it had a number of advantages. It burned with virtually no smoke or flame, producing a very strong and stable heat. It was used for more delicate cooking processes requiring precise temperature control, such as when working with roasting pans. Later, especially in castles in the northeast of England, coal delivered by sea from the Newcastle area began to be used as fuel, which is why it was called sea coal. However, it emitted acrid, sulfurous smoke, so its use in cooking was limited mainly to heating closed boilers. However, in order to heat huge ovens, a completely different approach was required, based on accumulation rather than constant burning. We will explain how it works shortly. In addition to large hearths, bread ovens were an essential feature of castle kitchens and often of separate buildings called bakehouses. Archaeological finds in castles such as Goodrich and Helmsley show that these were separate, massive structures that worked on the principle of accumulated heat. Unlike a fireplace where food is cooked over an open fire, a dome oven or oven was first heated from the inside, and then its heat was used for baking. The design was ingenious in its simplicity. Thick walls and a beehive-shaped vault ensured maximum strength and even distribution of radiant heat. Often the oven had double walls, and the space between them was filled with sand or gravel for additional insulation, which allowed the heat to be retained for an incredibly long time. The foundation under such a structure had to be extremely strong to support the weight of several tons of stone and brick. The process was as follows. Inside the oven in its main chamber, with a floor made of fire bricks or clay slabs, a large number of bundles of brushwood, faggots, were laid and set alight. Faggots were used instead of thick logs because they produced a quick and intense flame, which was necessary for effective heating of the stone mass, and did not leave large, long smoldering coals behind. The oven door was left open for draft. The wood burned for several hours, heating the inner walls to white hot. An experienced baker determined when the oven was ready not by time, but by the color of the stones in a simple test. A pinch of flour thrown on the bottom should quickly turn brown, but not burn to a crisp. When the oven was hot enough, all the coals and ashes were completely removed with a long rake. Then the inner surface of the hearth was wiped with a special scovel or malkin, a bundle of wet rags on a long handle, to remove any remaining ash and create the steam necessary for the formation of a crispy crust on the bread. After that, the oven was ready for use. Using a long wooden shovel peel, bread was quickly placed in the hot chamber. From the exquisite white bread, manchet, made from the finest flour for the Lord's table, to the simpler rye or mixed bread maslin for the garrison and servants. Sometimes this simple bread was used to make trenchers, thick slices that were used as edible plates. Then the mouth of the oven was tightly closed with an iron door or simply blocked with a stone, and the cracks were sealed with clay to ensure airtightness. Now the cooking process was carried out exclusively by the heat accumulated in the walls. Bakers were masters of the falling oven concept. After baking bread, which required the highest heat, pies and casseroles were cooked in the cooling oven, and then, at an even lower temperature, porridge could be slowly simmered or fruit and herbs dried. In this way, a single firing of the oven allowed it to be used for many hours, which was very economical in terms of fuel consumption. In addition to active heat sources, the architecture of the kitchen itself played a huge role in heating, functioning as a passive heating system. This principle was based on the physical property of stone, its high specific heat capacity. Unlike wood, which heats up quickly and cools down quickly, stone absorbs heat slowly but in huge quantities, and then releases it just as slowly. The walls of the castle kitchen were built from local stone, either sandstone or limestone, and were up to 1.5 to 2 meters thick. The floor was also laid with massive, roughly hewn stone slabs called flagstones. These surfaces served as giant passive heat accumulators, as evidenced by traces of thermal cracking on the stones found by archaeologists near the remains of ancient hearths. Throughout the day, the stone walls and floor absorbed a huge amount of radiant energy from the working hearths and stoves. This process was slow but continuous. The stone, with its high thermal inertia, accumulated heat, preventing the room from overheating during peak fire activity. At night, when activity in the kitchen subsided and the flames in the hearths diminished, the reverse process began, which can still be observed today in old stone buildings. This effect was especially important for the comfort of the staff. Working in the kitchen was hard physical labor, and a stable temperature without sudden changes allowed them to maintain their productivity. Warm floors, in particular, were not a luxury but a necessity for people who spent 12-14 hours on their feet in simple shoes. The stone walls and floors, heated during the day, began to slowly and evenly release the accumulated heat into the surrounding space. This not only created a stable temperature, preventing the kitchen from cooling down completely overnight, but also served an important hygienic function. Kitchen floors often had a slight slope toward a central drain, sump, which allowed waste and grease to be washed directly onto the floor. The constant heat emanating from the stone helped the surface dry quickly, preventing the formation of slippery and dangerous dampness and mold growth. Moreover, this passive heating system worked in synergy with ventilation. The heat radiated by the floor and walls warmed the lower layers of air, enhancing convection currents and helping to push smoke and steam upward toward the louver in the roof. In this way, the entire building structure functioned as a single, self-regulating thermodynamic machine. This passive heating system was extremely efficient because it required no additional fuel costs or effort. It was an integral part of the building's design. However, many cooking processes required not only high temperatures, but also hot water in huge quantities. We will explain how this problem was solved below. Constant access to large volumes of hot water was not just a convenience, but an absolute production necessity on which the speed and hygiene of the entire cooking process depended. Cold water was practically useless in dealing with the grease that covered the dishes, tables, and floors in huge quantities after cooking meat dishes. After a large feast in the castle, hundreds, if not thousands, of dirty items could be left behind. Wooden and tin plates, knives, spoons, cups, huge serving dishes, and of course, the kitchen utensils themselves. Washing all of this required a constant stream of boiling water capable of emulsifying grease. Soap was not used as a cleaning agent, but rather abrasives such as sand, ash, and sometimes bundles of field horsetail, whose hard stems, rich in silica, acted as natural sandpaper. The effectiveness of this cleaning method depended directly on the availability of hot water. In addition, boiling water was used to scald poultry carcasses to make them easier to pluck, to blanch vegetables, and to soak salted meat. Carrying buckets of water from the hearth would have been a logistical nightmare. So castle kitchens used a stationary system known as a set pot or built-in boiler. These were huge containers, most often made of copper alloys such as bronze or copper itself. Copper, with its high thermal conductivity, allowed water to be heated much faster and more evenly than cast iron, which was also prone to rust, spoiling the taste and color of the water. Such a boiler was a valuable asset, often mentioned in castle inventory lists, and was installed for centuries. It was carefully placed in its place, after which a special brick or stone base was built around it. Under the boiler was a separate firebox with a cast iron door and a blower to regulate the airflow, and accordingly, the intensity of combustion. The firebox had a separate small chimney that opened into the general ventilation system. This design allowed the water in the boiler to be kept hot or boiling throughout the day, regardless of the operation of the main hearth. Archaeological finds show that the volume of such boilers could reach 400 to 500 liters. It was, in essence, a dedicated water heating station that ensured the smooth operation of the wet zone of the kitchen. The source of water for this giant was usually the main well of the castle or a cistern. Filling the boiler was one of the most difficult and monotonous duties of the junior kitchen staff, the cooks or scullions, who carried dozens of buckets of water from morning to night. Their work was cyclical. Bring cold water, scoop out the hot water, take it to the scullery, pour the dirty water down the drain, and go back to the well. The presence of a stationary boiler greatly simplified many processes. In the richest and most technically advanced castles, such as Windsor Castle during the reign of Edward III, primitive lead pipes could run from the boilers. They were equipped with a simple tap or spigot, which allowed hot water to be poured directly into stone or lead sinks. These sinks were located in an adjoining room, the scullery, which was the epicenter of cleaning and washing. In most cases, however, water was simply scooped out of the boiler with long ladles and carried to wooden tubs and stone sinks. This system was, in essence, the prototype of the modern industrial boiler and was one of the key elements ensuring the high productivity and smooth operation of the castle kitchen. Despite the fact that the kitchen was the hottest place in the castle, its space was not chaotic, but strictly organized according to the principle of thermal zoning. This was not a whim, but a pressing necessity dictated by the logic of preserving food and building an efficient production process in a constant struggle against the two main enemies of medieval provisions, spoilage and pests. The intersection of temperature zones or improper storage of ingredients inevitably led to their spoilage, which was an unacceptable loss in the context of medieval logistics. The entire kitchen was designed as a production line, where products moved from cold storage to hot processing. This system was not just a set of rooms, but a physical embodiment of the medieval order, where each product and process had its own strictly defined place. The hottest area, the engine room of the kitchen, was located around the large hearths and ovens. The air here was saturated with heat, steam, and the smells of food being prepared. This is where the spits, cauldrons, and everything related to direct heat treatment were located. Nearby, but at a safe distance, were tables for the final serving of dishes known as dressers. These were long, massive tables that served as the last line of defense and stage before the dishes were served in the Great Hall. Here, the finished dishes, removed from the fire, were placed on huge silver or pewter serving dishes. The senior servant, the sewer, inspected each dish here before giving the order to carry it to the hall. This was the final quality control and, at the same time, the beginning of the serving ceremony. Next came the moderate zone. Here stood massive oak tables and blocks on which preparatory work was carried out: cutting meat, cleaning vegetables, kneading dough. The temperature here was lower, which made the working conditions more bearable for the staff and prevented the food from heating up prematurely. Here you could find stone mortars and bronze pestles for grinding ingredients, boards for rolling out dough, and a whole arsenal of knives and cleavers. The cold zone was the most important in terms of logistics and storage. It consisted of several highly specialized rooms, usually adjacent to the kitchen on the north side, which was the shadiest. The larder, from the French lard, fat, was a storeroom for meat. There was often a wet larder with a stone floor, which was sometimes sprinkled with water to maintain the coolness and humidity ideal for fresh fish and dairy products, and a dry larder with good ventilation for storing salted and dried meat, bacon, and sausages. Hooks hung from the ceiling, on which carcasses were suspended. Pantry, from pain, bread, was a room under the authority of the pantler, who was responsible for bread. Bread, flour, salt and table linen, tablecloths and napkins were stored here. The key requirements here were dryness and protection from rodents. Buttery, from butt barrel, was a room under the control of the butler, where barrels and jugs of ale, beer and wine were stored. Coolness and darkness were necessary for the proper storage of beverages. Both the butler and the pantler were key figures responsible for accounting for and dispensing vital supplies. Spicery, a separate, often locked room for storing precious spices such as pepper, nutmeg, and saffron, as well as sugar and dried fruit. It was more of a safe than a pantry. The clerk responsible for it, the spicerer, dispensed spices to cooks by weight using small, accurate scales, as the cost of these ingredients was comparable to that of precious metals. The pinnacle of refrigeration technology was the ice house. It was a deep underground structure lined with stone or brick, where ice harvested from rivers and lakes was brought on sleds in winter. The ice was packed tightly, sprinkled with straw and sawdust for insulation, and drainage was provided at the bottom for meltwater. Such an ice house could keep ice cold until the end of summer and was the ultimate symbol of luxury, allowing chilled drinks and desserts to be served at the table. The clever layout of these areas, in relation to each other, turned the kitchen into a kind of conveyor belt and was the basis for its smooth operation. Heat production was only half the task. The other, equally important half was its efficient and controlled application. For this purpose, a whole arsenal of mechanical devices was used to precisely control the cooking process over an open fire. These devices, found during excavations at castles such as Tanelon and Dorn, demonstrate the high level of medieval engineering ingenuity. They were not designed for convenience, but for precision and safety when working with intense heat. The main tool for roasting meat was a spit. In large hearths, massive forged metal spits several meters long were used, which were mounted on heavy cast iron stands called andirons or fire dogs. Turning such a spit by hand was tedious and monotonous work, often performed by the youngest of the cooks, the turnspit, who would sit for hours by the red-hot fire. This position was considered one of the lowest in the kitchen hierarchy, requiring tremendous endurance in exchange for minimal pay in an atmosphere filled with smoke and hot grease. His sole task was to maintain a constant, slow rotation speed so that the meat cooked evenly, without burning on one side or remaining raw on the other. Therefore, mechanical drives known as spit engines eventually appeared in wealthy castles. The most common mechanism worked on the principle of a clock. A heavy weight, often a stone or lead, slowly descended, transmitting rotation to the spit through a system of cables and gears. The speed of rotation could be adjusted by changing the weight of the load or the gear ratio in a primitive reducer. This was advanced technology for its time, freeing human labor for more important tasks. A long dripping pan was always placed under the spit to collect the dripping fat, which was constantly poured over the meat with a long-handled spoon to keep it juicy. This collected fat was a valuable byproduct, which was then used for frying other foods, adding to baked goods, or enriching the flavor of soups, ensuring that no part of the valuable product went to waste. A system of swivel taps and hanging hooks was used to control the cauldrons and other utensils over the fire. A massive metal bracket, known as a chimney crane or sway, was built into the wall of the hearth and could be rotated like a lever. This simple device was a huge step forward in occupational safety. It allowed one person to safely move a pot that could weigh more than 100 kilograms, including its contents, away from the fire or, conversely, place it in the hottest part of the fire. A key element of temperature control was a suspended hook called a trample hook. It consisted of a metal plate with notches or a system of several S-shaped hooks, which made it possible to adjust the height of the cauldron above the flame with an accuracy of a few centimeters. By raising the cauldron higher, the cook could switch from a violent boil to a slow simmer, which was critical for preparing sauces and complex stews. In addition, the arsenal included gridirons on legs for roasting fish or poultry over coals, trivets for placing pots directly in the ashes, and countless forks, flesh hooks, skimmers, and pokers with handles up to 2 meters long, allowing one to work with fire from a safe distance. Despite all the engineering ingenuity, the main element controlling the heating and operation of the kitchen was the human being. At the head of this complex production process was the head chef, referred to in documents of the time as the master chef, magister cooks, or master cook, or in some cases the kitchen sergeant, sergeant of the kitchen. He was not just a cook, but a highly respected manager, logistician, and heating engineer all rolled into one, whose skills were held in extremely high regard. His status is confirmed by documents such as the Form of Curie, a 14th century recipe book compiled by the chefs of King Richard II, which demonstrates the incredible complexity of court cuisine. These recipes required not only rare ingredients, but also complex multi-step cooking techniques that were beyond the reach of a simple cook. The head chef's responsibilities included strategic planning. He drew up the menu based on the liturgical calendar, fasting and feast days, seasonal availability of food, and, importantly, the status of the castle's guests. The menu for the Duke differed from that of the Baron in the complexity of the dishes and the value of the ingredients. He kept strict records of all resources in the storerooms, from barrels of wine and ale in the buttery to flour supplies in the pantry and the most valuable spices, which were kept under lock and key in a separate spice room. He was responsible for purchasing food, controlling its quality and quantity. A strict hierarchy worked under his supervision. The saucier was responsible for sauces, the baker for bread, and at the bottom was an army of cooks and scullions who did the dirty work. The most difficult task was synchronization. A medieval feast consisted of several changes or services, courses, each of which included dozens of different dishes served simultaneously. The head chef had to conduct a complex orchestra like a conductor. He calculated the start time for each dish, whether it was a roast that took hours on a spit, a pie in the oven, or a sauce that required several minutes of concentration, so that everything would be ready at the same time. Without clocks or thermometers, he relied solely on his experience and senses. The color of the stones in the oven, the sound of boiling broth, the smell of meat cooking. This intuitive control panel, based on years of practice, was his main tool. He managed a staff that could number up to 100 people in the royal kitchens, giving instructions in a loud voice to be heard above the noise and din of the working kitchen. Not only did the quality of the food and the Lord's reputation depend directly on his competence and ability to manage this complex thermodynamic system, but so did the smooth, efficient, and safe operation of the entire kitchen complex. The medieval castle kitchen was not just a place for cooking, but a complex, well-thought-out, and in its own way ingenious engineering complex. From moving the building outside the walls for fire safety to passive ventilation systems and the thermal inertia of stone, every element was subject to a strict logic of efficiency and survival. It was a world where controlling fire required no less skill than wielding a sword. Which of the engineering solutions you saw today struck you as the most ingenious and unexpected? We would love to hear your thoughts in the comments. If you are interested in similar in-depth analyses of historical technologies, subscribe to our channel. There are many more obscure topics to come.